Developing on the cloud is complex. What if you could use your existing programming knowledge to build, deploy, and manage cloud infrastructure using your favorite languages and tools? Pulumi is a cloud engineering platform that lets you write infrastructure as code in any programming language and on any cloud platform. If you're an Azure fan like me, then you'll love Pulumi's integrations with the Microsoft ecosystem. You can use .NET to define infrastructure from your favorite IDE like Visual Studio and deploy with Pulumi's CLI or with CI/CD like Azure DevOps. Pulumi uses the same APIs as Azure Resource Manager, so you get access to all of Azure's capabilities. Plus, it's open source. Get started with Pulumi for free today at pulumi.com. That's PULUMI.com. Hi, I'm Scott Hanselman, and it's another episode of Hansel Minutes. Today I'm talking with Luis Ceze, Dr. Luis Ceze, who is a professor at the Paul Allen Computer Science and Engineering School at UW, as well as the founder of and CEO of OctoML. How are you, sir?
Good. Thank you, Scott. I've been looking forward to this. Excited to be on your show.
That's very kind. So 2 full-time jobs.
That's right. Yeah. They're very synergistic. So I promise I'm not hyper distracted yet. A lot of the work that led to OctoML started at the University of Washington, and the open source project called Apache TVM started there 5 years or so ago. And then a lot of the folks that were involved in the project co-founded the company with me. I've been spending most of my time at OctoML these days. So,
and this is a thing that's encouraged. This is actually your second spin-off from UW CSE, correct?
Correct. Yeah. We make mistakes and we learn and do it again and we do it better. So,
and is that something that's encouraged when you're a faculty and you've got a PhD and you're doing postdoctorate work, you're doing research, and you come up with an idea, like it may be founded, your PhD work may be, funded by other companies, but then you can go and spin off a company. How does that work? How do you keep track of all that?
Yeah, absolutely. So, it's encouraging. I see, building companies around research work is a great way to have impact, when there's many ways to have impact with research, right? So you write papers that people read and do follow on research. Students graduate and become professors and do their next thing. Or, when the research is timely and, has just prime for impact in industry today. We form companies, and luckily OctoML has been going extremely well. So
very cool. Before we get into OctoML and Apache TVM and what they do, I want to take a moment. I want to back up about 5 years because I read a paper that you worked on with the Computing Community Consortium that was called Arch 2030 or Architecture 2030. It's a vision of computer architecture research over the next 15 years. And here we are 1/3 of the way into the predictions that you were making in this paper here, which I think it's only 12 pages. It's worth reading, but I think it'd be useful to talk about those things and see how close you were, because machine learning was a big part of that.
Right. Yeah, absolutely. So yeah, that paper was really, really interesting and fun to write. It was a result of a workshop that I co-ran with my colleague, Tom Wenish, and spearheaded by Mark Hill. The way I see computer architecture, just to back up, that's my home community in computer science. Computer architecture is really about how do you build systems? How do you put hardware and software together to enable new applications and to continue making computers better, faster, more energy efficient, and so on. And that's, and in Architecture 2030, we have a few points there. One of them was, deeper 3D integration. This is definitely happening. And it was already clear then, and now it's only deepened. You start to see what we call 3D chips, where you put memory close to compute, and you no longer lay out chips into dimensions, start laying into dimensions. And this is, in fact, becoming commodity. Another one's computing closer to physics. I'm sure you've seen a lot of news and results on quantum computing that becomes ever closer, and also using DNA for data storage, using molecular storage as an alternative to electronic storage, magnetic tape, and so on. Then using data centers as a big abstraction. The reason I meant, we use that is that data centers are just the perfect encapsulation to put different specialized hardware and offer an interface to the rest of the world that is clean and, abstracts away this complexity. And this is it started happening, for real now. TPU, Google, went all in with TPU. Microsoft deployed FPGAs, and, Facebook had, being known to be building hardware as well. So data centers becoming a clean abstraction for, hyperscalers to deploy new computer architecture innovation is also happened. And then finally, machine learning as a key workload. I think it's just fair to say that it was very clear then that machine learning was consuming a large and ever growing fraction of the compute cycles and the compute resources in the world, and that only intensified. That's both true in edge devices, in devices like phones, smartwatches, smart cameras, as well as, data centers as computers have been spending a larger and larger fraction of their cycles in machine learning. A notable example are models like GPT-3, right? So just giant language models that are spookingly effective. They use an incredible amount of computation. So, and they are incredibly good. So that means people are going to want to use them. So the question is, how do we do that without using too much energy, or and even being able to scale, large enough to serve the world, right? So I don't want to say we were right in all of them, but I would say that 5 years in, the only thing I can think of is that we could have been even more ambitious, because I think it happened faster than we had expected.
that point that things have happened faster than we expected, I think, is a really interesting one, because if we reflect on when did the cloud start, arguably we could say March of 2006, kind of the inception and the launch of AWS. That was only 15 years ago, right? Like even iPads are only a couple of years old if we don't count the ones they used in Star Trek: The Next Generation. Right. So in 15 years, all of these things that no one was thinking about happened. Machine learning was nascent and then went straight up. Yeah. And now we're seeing it everywhere, and we'll talk about that. Deep 3D integration, virtual reality wasn't a thing that we could think of, and any other than everything was a niche. All these 5 niches popped all at the same time. The one that I think is the most interesting that then drives ML is the idea of the cloud as the place to abstract, have architecture, innovation, abstractions. Like the cloud for me in the old days was just other people's computers. It was hosting. Yeah. But now it is elastic, and a lot of young people and early in career people have never seen the cloud. They've never racked a PC. Yeah. So their sense of a cloud is a slider bar or a checkbox somewhere.
Right. That somebody pays the bill for, right? So yeah, absolutely. I haven't taught a class in a while, but one of the things that I loved doing with the computer architecture students was to take them to a data center to see what the cloud actually is, and seeing the physical racks and the scale really puts in back to it. But I would say there's just one more thing. It's not just other people's computers, a bunch of computers inside the building. These are now becoming computers with highly specialized hardware that you would not have physically close to you. Like, the type of specialized silicon that we're starting to see in data centers is not the same specialized silicon that you see in edge devices. So these are purpose designed to be in data centers and to be racked very close together and to be hyper dense and hyper efficient for that purpose. That's really the point that we made there, was the cloud, being an abstraction for new hardware was pretty clear. Can I talk about one trend that we missed though?
Please.
So using AI and machine learning for better systems design, and even AI and machine learning for better AI and machine learning. So basically the key thing that actually happened, and it will tie back to TVM as the conversation takes us there, is I think this idea of using machine learning to improve systems themselves, and those systems can be systems to run machine learning, happen also super fast. And I think that showed effectiveness very quickly. And all of a sudden we're actually using, mainstream systems today that have been, in a large part optimized and in parts designed by machine learning. So
there was actually an article in Anand-Tech in June where they were talking about using AI to build better processors and going and applying it for, traditionally board designers use everything from science to engineering to for loops to decide how to lay things out appropriately. And now they're throwing AI at it, and they're popping out with chip designs that no one had ever thought of. Is that the beginning of the snowball that's going downhill? It's going to turn into an avalanche and crush us all.
Yeah, it's well, how about this going to be the beginning of the scene that gets better and better, and all of a sudden we all lead happy and productive and and healthy lives, So
I like that positive attitude. Is that the thing? Let me rephrase. Is that the thing that means that Moore's law starts back up again, and we can actually make exponential improvements, or are we hitting the laws of physics?
Or we're definitely getting close to laws of physics in the way we build computers today. But this might be probably a topic for a whole entirely separate conversation, but non-CMOS, non-electronics based type of substrates for computing are starting to become, not only more attractive because, we're reaching the limits of electronics, but also more viable. And I firmly believe that the rules of design and the way we think about designing with those different types of substrates are only going to be possible with AI and machine learning, because it's just way too complex for doing the kind of engineering that we've been doing so far.
So there's two things that I want to dig into then. First, let's talk about machine learning and specialized hardware, which you touched on a little bit. And then at some point, I want to try to catch and discuss on what happens when we don't understand the things that we're making, when they are truly black boxes, even to the PhDs and the postdocs. You mentioned that the cloud as an architecture abstraction for specialized hardware. Like if I want a GPU, I can try to get one from a Bitcoin miner and do it locally here, but I'm never going to be able to have the kind of specialized hardware I can get in the cloud. So I'll use a GPU farm. But you're talking about real specialized hardware. We think about CPUs and GPUs. There's machine learning optimized chips coming
that's right.
and exist now.
Yeah, absolutely. Machine learning optimized chips is already there. And chances are that you're using applications that use them indirectly. There are also chips for encoding and decoding videos at scale, for example, that happens all the time, and audio and so on. There's cryptography hardware, and these are all types of specialized silicon that exists in the cloud because there is an extreme need for efficiency that honestly, the only way that's possible right now is by having specialized hardware. So, to the point of machine learning being a dominant workload, machine learning becoming a dominant workload and using a lot of cycles and therefore, using a lot of energy and not being cost effective for the large service providers, going to specialized hardware is a question of needs, not just a question of nice to have. I think it's fair to say that many services that we use at scale today already would not be possible without some deep form of hardware specialization that already happens today. And GPUs are a form of that too, by the way. So even though GPUs are getting more and more specialized aspects in the architecture that are tailored towards machine learning workloads, right? So,
Are you under increasing pressure to ship code faster than ever before? Then it's time to work smarter with Raygun's modern approach to error and performance monitoring. Raygun gives you instant visibility into the health of your software. And what makes it so unique is that it not only tells you when something's gone wrong, it shows you exactly where it's gone wrong and how to fix it, right down to the line of code. Made by developers for developers, Raygun has built a suite of monitoring tools that are used and loved by thousands of software teams every day. You can monitor every corner of your tech stack with widespread language support and native integrations with GitHub, Jira, Slack, Bitbucket, Octopus Deploy, and more for even greater visibility. Visit raygun.com to resolve issues faster and to deliver flawless digital experiences for your users. That's raygun.com to get started on your free 14-day trial with plans starting from as little as $4 a month. raygun.com. So as a dabbler, a hobbyist, even from the machine learning perspective, I can train small models and I can play with them and I can share them with my friends, zip them up and send them off. But they are tiny little simplistically trained black boxes. And I'm not thinking about compiling them. I'm not thinking about targeting them. I'm not thinking about making them run on specialized hardware. They're just simplistic little models that I send around. What is the need for a compiler and for specializing? And then what is Apache TVM and what does TVM even stand for?
All right, cool, great. Oh, there's a lot there. So I'm gonna try to be efficient here. So, first, why even thinking about compilers in machine learning? First of all, it's just a question of making better use of the hardware, right? So as models become more and more sophisticated and put more demands in the compute cycles and the and storage in these devices, you need to be as efficient as you can, to in using them. Otherwise, you might not be able to do interesting things with it, right? So, and if you use the typical default paths that you're probably using for your simple models to deploy, you're leaving an extreme amount of efficiency on the table. Think of it as 10x, 20x, possibly 50x. Okay, so, and that's we can make a quick analogy to running a Python script without being compiled using only interpreter versus running a compiled version where you see an extreme gain in performance just because you're specializing the actual machine code to what you're trying to do, as opposed to running machine code to interpret something. And this has inherent inherent inefficiencies. A very quick example here is that you're going to have a lot of code that's asking the question, should I do this or that or that or that, depending on the data, as opposed to just writing machine code that knows what you want to do and just does that without even asking the question what should be doing at that time. That's one example. There's a bunch of other things that, are fun to think about, but I don't want to bore folks in the show here, but how you distribute data in memory, how to actually lay out the data in your models in memory has a huge impact on performance. And doing that right requires a fair amount of manual tuning, right? So, anyways, is that clear why compiling then is? Because otherwise you're leaving a lot of performance on the table. And we just talked about how important efficiency is, especially for machine learning workloads. So,
seeing if I can paraphrase it back, because I kind of know how our audience thinks. If the audience thinks about, CISC, complex instruction set systems, and you might say, well, this instruction set was added in this version of the Intel Core processor that didn't exist before. If I'm running 10-year-old code that's unoptimized, that doesn't know that instruction set exists, it's going to do the least efficient thing. They're like, wait a second, we built this into the silicon. We've got an instruction set for that. Change a linker, put in a compiler flag, fire that thing up, and that for loop or that instruction that was in the past done inefficiently is now done in the silicon, in the rock itself. So if I'm going to be going to really specialized, specific chips, I'm absolutely going to want to exploit everything that they can do in the silicon and do as little as possible outside.
Yeah, and not only that, not just for specialized silicon, but even for CPUs and common CPUs and GPUs too, because the inefficiencies that we're talking about in a general purpose processor going to specialized hardware also exist when you're talking about the general purpose interpreter of your model versus, specialized code to run your model, right? So even if you ignore specialized hardware and you ignore GPUs, just let's say just plain old CPU, it's a huge amount of performance on the table that's left behind if you don't apply, things that you normally do in code optimization, model optimization, right? So, and so switching to TVM. So is that okay? Can I?
Yes, sir. I want to know. I did all my research. I opened up 1,000 tabs. I took notes. I can't find out what TVM stands for.
Tensor Virtual Machine. It was a test. It was there somewhere. No, yeah, you're right. It should even be more clear. It stands for Tensor Virtual Machine. And acronyms can evolve, but basically, what TVM is, the spirit of what's a virtual machine, right? It's creating a clean abstraction over a variety of hardware targets: CPUs, GPUs, specialized hardware, FPGAs, small, tiny CPUs, big server CPUs, small GPUs, big GPUs, and so on. Create a clean, unified, single abstraction for one to map machine learning models to. Okay, so, and doing it in a way that makes the most out of the hardware where these models are going to run on, right? So the state of affairs today in the machine learning technology landscape, let's say industry and academia and so on, is just that it is a bit like the PC industry in the 80s. There's tight coupling between hardware and software, right? So, and, there's vendor specific software stacks, there's use case specific software stacks. And then for you to be serious about deploying machine learning, either in the edge or in the cloud, you need to navigate this very complex, set of options for you to get your model to run the way you want them to run, on your target device. And it's a huge impediment to machine learning model deployment, in a way that is efficient enough and scalable for wide deployment, right? So what TVM does essentially, it abstracts that away into a single path from the high level framework down to the deployable module, to the bits you want to deploy in the hardware. Right. So TVMs ingest models written in TensorFlow, PyTorch, MXNet, or it can be represented in common representations like something called Onyx. And then it translates to an internal representation that's the same across all hardware. There's a bunch of high-level optimizations, essentially fuses part of the code, lays out the data in different ways. It can do things like quantization, which is reducing the precision needed. And then it produces codes to the specific hardware target automatically without requiring hand tuning. Today, machine learning is very much at deployment phase, very much based on hand tuning of the resulting models and the resulting code. TVM subsumes all of that with a machine learning based engine to generate machine learning code. So it learns about the hardware that it's going to run the code on by running a bunch of little experiments, build a personality of how the hardware behaves, and uses that to guide the code generation and the optimization. So,
is that something that happens just in time, or is that now a library of understanding that is sent done a priori of all of those different available endpoints?
That's an excellent question. So if you install TVM fresh off of GitHub and you have to go and run that yourself, have to kick it off to run the experiments and do the tuning. At OctoML, we do that ahead of time and get it ready to go for users of our platform. And also TVM is very much, a machine learning engineer's tool. It's a sophisticated tool to use, right? We made it turnkey with the cloud platform and so on, but that's an aside. So let's just focus on TVM. Yeah. So TVM can either do it ahead of time and you have this library of things that you learn about the hardware to use for future optimizations, but it can also be done on the fly just in time to optimize the code, right? The reason you might want to do it ahead of time is that you might not have the resources to do it just in time. So you want to do it ahead of time, get it ready, and then just deploy the result, right?
Mm-hmm. Okay. And just for context, going back a little bit for the audience who may not be following all the different words and acronyms, right? A tensor is this mathematical object. Many of us heard that word first, who did not do math degrees, when we heard of TensorFlow, right? It's an array of numbers. It transforms according to certain rules, and it describes a point, and it kind of is part of this tensor field, right? And tensor virtual machine, as you just said, abstracts away a lot of things, giving us a nice thin layer. So we talk to that TVM and everything underneath it is abstracted away. So then OctoML is the company that you've spun off that is a value add that makes that accessible to regular people, hopefully like myself.
Yeah, regular people. We make it much more automated, accessible via a nice web interface and an API. Allows you to benchmark to see how your models are doing in the edge. Allows you to benchmark how to give the least amount of money to the cloud providers to make sure you squeeze the most out of the hardware, right? So in some cases, you offer 10x better throughput per dollar to allow the service to scale further. And not only that, I mean, one of the things that I hope I'm not going to be overly dramatic here, but we can't forget that if you make something 10x faster, you make it use 10x less energy. So even if you don't need to, it's just the right thing to do to save energy, right? So you don't need to. So the fact that we can make it faster in an automatic way means that you were wasting resources before.
Yeah. Yeah. I mean, to scale something, I always joke about this when I'm teaching my students, is if you want to scale infinitely, you have to do nothing. And once you do nothing, you can scale that infinitely, right? So the less you do, the more you can do, right?
Right. And the less you do and produce the same results, you should do that. The question is how much engineering is required. And we are automating that engineering by applying machine learning. That's really what, OctoML and Apache TVM is about.
Right. And you're trying to create this positive cycle of improvement. And that brings me actually to this idea of ML ops. We hear about DevOps and SecDevOps and now ML ops, right? This is that developer's kind of inner loop of making little improvements as they move it out to production. Where does ML ops fit into machine learning and OctoML?
Yeah, absolutely. So that's an excellent question. And ML ops is this kind of like evolving term, an evolving thing that has different interpretations by different people, right? So, so think of it, ML ops as how do you go from data to insight and models to a deployed machine learning model and module in the field doing something useful for the place. Let me give an example. If you are doing a atrial fibrillation detection for an Apple Watch, so what do? You collect a bunch of data about how hearts behave, right? So, and then you have to manage that data. There's a data management aspect. Okay. So, and then you curate the data sets to train your model, and then you develop your model. So now there's a model development aspect, and then you validate and test your model. And then once you're happy with it, you have to put into production to run your heart atrial fibrillation detection on an edge device, on a smartwatch. You have to now be able to match that model to the hardware that you're going to deploy for it to do its job. And then MLOps is all of this: data management for training data, the model creation, validation, and refinement, the model deployment management, the model compilation, optimization, the model packaging, the model deployment, and the model deployment management. It's really the way I see MLOps is really end to end. And honestly, automate that as much as possible, right? So, I would say that DevOps is an integral part of this because machine learning models are always, part of a bigger application. So, and that's part of DevOps in and of itself. So think of MLOps as the things that's specific to machine learning in the life cycle of deploying applications with machine learning code.
Right. And as you were listing out all of those kinds of things, and I'm thinking, oh, that's overwhelming. What MLOps and DevOps as a grandparent of that is trying to do is make our lives easier by automating all the boring stuff.
Yeah, that's right. Yeah, automate the boring stuff, and also making sure that you have the right tools to um, actually manage this complex beast that machine deploy machine learning is. Right. So we used
Mm.
to writing code, and we got really good at it, and there are tools for that. But machine learning is not just code. Machine learning is code and data that feeds into your model, and the
Mhm.
data evolves, and the world and the situations in which your machine learning is deployed evolve. So you have to continuously monitor how the model is doing and refine it to the environment. Right. So
Mhm.
and MLOps helps you with that too. So.
Okay. And then part of OctoML's products is the Optimizer, right, which is that commercial version of Apache TVM. And I read a really interesting case study here where you helped a company called Runway, which is actually like an online video editor, but behind it, they've got like 100 plus machine learning models for how they're
Yeah.
synthesizing images and video and text. And as with any startup, as you mentioned, of course, in the Arch 2030 paper, startups are trying to scale faster than ever before. They don't have to buy hardware, but they got to be efficient with their money, with their resources. Yeah. Runway is a startup, and they want to go and have real time ML and offline ML needs, and all of that's going to cost them money. So they need to do more with less.
Exactly. Do more with less. In the last years, less money to running the model at scale in the cloud, less compute resources to be able to deploy this, say, on an iPhone, and also less engineering resources, right? So the kind of engineering required for you to put a machine learning model into production is this rare form of software engineering coupled with machine learning knowledge, coupled with systems knowledge, coupled with, DevOps knowledge, right? So, and we want to automate that. In fact, we automate a lot of the engineering required to do that in our OctoML software as a service platform. So
yeah, and that idea, by the way, of focusing on what you're good at and letting them focus what they're good at, right? Because I'm thinking about if I'm a startup and I got this idea for like real time or next generation content creation, I don't want to worry about optimizing machine learning models. I just want them to work really well.
mm-hmm.
So the division of responsibility is good, and you just went in there and provided them 2x, 5x, 10x improvements on perf and size.
That's right. Without them having to go and fiddle with all those super complex tools. And by the way, so just as a minor correction, that it's not
Please.
the OctoML software service platform is not just Apache TVM as a service. It
Hmm.
actually underneath it can actually use other engines too. The vision that is a machine learning acceleration platform. You give us the models, and we're gonna get them ready for you for deployment. It might even involve using tools that are specific to your chip, just if that's the right thing to do, except it should be completely transparent. We want to abstract away all of the thorny, expensive headaches that people have in navigating how to get machine learning to deployment, right?
That's a great point.
Much in the same way that if you get a web server in the cloud and you just upload your workload and then whatever runs, you don't have to go and configure that. You don't have to do anything. Just upload your content and it's served, right? That's essentially the abstraction that we are developing here for anyone deploying machine learning models. So
right. Hence the implication of the octopus, where on this side I've got eight arms talking to all the different model formats, and on this side I've got all the different hardware and GPU targets, and the brain in the middle. And you're brokering that in any direction, the combinatorics, the Cartesian product of all the things that you could throw at it. You handle all that.
That's exactly right. Wow, thank you. That was fantastic. By the way, we have openings in our technical marketing team in case you are.
It's really just about me trying to understand.
Podcasting, right? No, absolutely. I know that was really awesome, Scott. Yeah.
Yeah. I'm trying to understand these things because that's really it's about abstractions. And as we mentioned at the beginning when we talked about the Arch 2030, it is getting the abstraction layers are getting deeper and deeper and deeper. When I learned, and I'm going to guess that we're not too far apart in age, when we learned about C and we learned about assembler, and we know where the electrons go when we write some code. But for a lot of early in career people who have come into software this year, those tools don't think about that. Like
they don't exactly, right?
We built cars and internal combustion engines, and they ride in Ubers. And they don't care about the abstraction layer. So the deeper it gets, the more of this is going to be hidden away from us.
Absolutely, yeah. And the more layers you have to abstract complexity, the more opportunities to reap benefits from optimizations, because an inherent trade-off in any complex engineering is you add abstraction layers that adds overhead such that you can actually manage complexity. So I think we're at a point where, we can automatically specialize and go deep down straight and remove all these layers. That's really what you, to go really full circle, is all these software layers involved getting your model down to the hardware that you abstract such that we can actually run your model. Now we can punch through that abstraction by generating super specialized code and hardware. And the way to do that is by using machine learning, because no human should be doing that. So
that's a really great point. And in all of this, we're boosting the performance. Like you said, it's free performance because we're not losing any accuracy. The model doesn't change. And that's really important point.
Yeah.
Right. This is not JPEG for machine learning where we throw stuff away. This is really efficiency.
That's exactly right. There's plenty of really important techniques in transforming the model and then trading off accuracy for better efficiency in the model. What we're talking about here is that once you have your model and you want to behave it exactly how you design it and make the most out of the hardware, that's where, Apache TVM comes in the picture. Really compile your model down. Yeah.
And that hardware, I was surprised to read, can be an ARM mobile or an embedded processor. I mean, things like TinyML exist. You could potentially run a model in an iPhone app if you wanted to.
Yeah, absolutely. In fact, you can run your models through TVM to deploy it on Apple devices and iOS. ARM is a big user and supporter of TVM and a partner of ours, right? So they've built a unified CPU, GPU, and their specialized hardware for machine learning using TVM. And you can deploy literally in something that's operated by a battery that can last many years to giant servers that uses tens of kilowatts, right? So
that is absolutely amazing.
And using a single abstraction. So,
all right. Well, thank you so much for chatting with me today.
Thank you very much, Scott. This is really fantastic. Thank you.
We've been chatting with Dr. Luis Ceze, the CEO and founder of OctoML. They are hiring and also a professor at the University of Washington. This has been another episode of Hansel Minutes, and we'll see you again next week.